Hi there, welcome back. This is The Logic of Risk, and as usual, I am Pasquale. Are you ready to take the risk? Let's go! In the first episode of this podcast, we defined risk as the possibility of a loss, namely an event with negative consequences, caused by internal and or external vulnerabilities and reasons which can potentially be mitigated at least in part, if not completely avoided. In the subsequent episodes, we focused on specific parts of this definition. We started with the concept of damage, highlighting how quantifying it is less straightforward than one might initially think. We emphasized the need to develop a damage profile and noted that we will soon see why this is necessary, namely why we need to look at damage from various perspectives, such as its nature, extent, and timing, in order to establish a basic starting point. Even during our discussion of the concept of damage, we questioned the idea that its measurement can be entirely objective, introducing the need for an axiological perspective that takes into account the evaluator and their value system. Remember that, at the end of the day, risk management involves transforming data and facts into values and judgments, and these are rarely objective. They depend on the individual and the context. I probably don't need to remind you how many things once considered acceptable no longer are today. Although there will always be nostalgics, we are fortunate not to distinguish anymore between the value of a slave's life and that of a free man, just to mention an easy example. Or at least we pretend not to distinguish formally, having abolished slavery, though many masks fall away when the death of a fellow citizen resonates more than that of an immigrant. After briefly examining damage, we turned our attention to the possibility of damage happening, looking at probability as one of the tools to manage this contingency. This led us to the various definitions of probability that we discussed together. If you haven't listened yet, I encourage you to do so. The underlying message is that there is no single definition of probability, that probability is not a monolith, nor a revealed truth carved in stone. Different schools of thought exist, each with its own dignity, and each more or less useful depending on the situation. Certainly, as I have said several times, I find the subjectivist view more coherent, and if you want, nothing stops us from seeing the others as special cases. In the end, when I choose to be a frequentist, I'm expressing a personal preference, so the frequentist approach can easily be seen as a particular manifestation of my being a subjectivist. What's important is to remember the aspect of choice and not assume that the limit frequency or propensity or logical definition is truth with a capital T. I know I'm repeating myself, but if we don't get that through our heads, everything else might as well go down the drain. Returning to our definition of risk, we still have some essential elements to address, identifying internal or external vulnerabilities and reasons, and devising strategies to mitigate or even avoid risk. That's what we will be focusing on from now on. To do so, we need to refine the tools at our disposal, tools that are essential for carrying out the four key tasks of risk management. Task number one: identify risks. Task number two: quantify them. Task number three: prioritize them, that is, create a ranking of risks based on acceptability and available resources to address them. Task number 4, communicate clearly and efficiently. If you think about it, in these last weeks of podcasting, we have covered a lot of ground, which I hope has been interesting for you. Considering that the best is yet to come, make yourselves comfortable because I still have many hours of rambling stories for you. Today, we are going to take a small step forward and begin talking about risk in a more formal way. For instance, we will try to understand more about risk measures, those mathematical statistical constructs that allows us to quantify and rank risks. Under the common definition of risk measure, we find many quantities that I'm sure you have already encountered in your studies or at work. We can mention, for example, the various means, from arithmetic to geometric, the median, the mode, the standard deviation, the variance, the value at risk, the expected shortfall, and so on. If you don't know them, don't worry, we will redefine them when we need to use them. To be precise, we can distinguish between positional measures, such as the mean, the median, and the value at risk, which help us get a sense of the order of magnitude of the quantities involved, and dispersion measures, those like the standard deviation, the variance, or the absolute mean deviation, that tell us how variable and volatile those quantities of interest are. I use positional in a rather general way, including location measures, not to be too specific. Purists will excuse me. In quantifying risk, a positional measure will allow us to estimate, for example, the average potential loss, while a dispersion measure helps us understand how reliable that average potential loss is in reality. Before we delve into some formalization, how can we define a risk measure in general? A risk measure, as the name suggests, is something that allows us to measure risk, that is, the possibility of a loss, of a damage. In other words, it is a tool that transforms a potential risk into a number that we can then use for our evaluations. Mathematically, a risk measure is a function mapping from the space of potential losses to the extended real numbers, that is, the set of real numbers plus positive and negative infinity. Indeed, in some situations we want our risk measure to be infinite, and we will later discuss what that means. Very often, to simplify matters, we limit the extended real numbers to the non-negative portion. It's a trick to eliminate those pesky minus signs from negative numbers that often make us mess up calculations. Let's put it that way. In the end, if we have a financial loss of, say, minus £1 million, what interests us is the size of the loss, its magnitude, that is, £1 million. The minus sign is just an accounting convention which we can ignore until we need to write a report, file a balance sheet, and so on. In short, we remove the minus sign to simplify calculations and put it back later when we are done. Let's start putting some order into what we have said so far, introducing some technical terminology. Mind you, this isn't just a quirk, it's the necessary precision to do our job well. Imagine we are pastry chefs. Sure, you can try baking by eye and maybe some desserts will turn out reasonably well, but the best recipes require extremely precise measurements and procedures followed to the letter. That's the only way to create desserts that truly leave a mark. If you didn't know it, cooking is my main hobby. If you recall, we talked about the sample space, or state space. We defined it as the fundamental set that contains all possible single outcomes of a random phenomenon. In probability, it is customary to denote this space by the Greek letter omega in its uppercase form. We also mentioned the event space, that is, the set of all the events that a random phenomenon can generate, essentially the set of all single outcomes and all possible combinations of single outcomes. In our now classic example of a die, the sample space contains the numbers 1 through 6, while the event space includes all the additional combinations we can define beyond the simple outcomes. For example, the triplet 2, 4, 6, representing even rolls, or the triplet 1, 3, 5, representing odd rolls, or the four-element set 1, 2, 3, 4, representing the outcome less than or equal to 4, and so on. As you can see, the number of elements in the event space is substantially greater than that in the sample space. Yes, it may seem trivial, but formally proving these facts may involve Cantor and cardinalities, which is a treacherous terrain we will avoid for now. Let's consider a manageable example. Imagine that our random phenomenon has three possible simple outcomes, which we denote as A, B, and C. The sample space will then have three elements, A, B, and C. Now imagine taking all the subsets of the sample space. Which ones are they? Well, certainly the single outcomes A, B, and C, but also the pairs AB, AC, and BC, as well as the triplet ABC, which represents all possible single outcomes of the sample space as a whole, that is, the entire omega. To this list of 7 elements we add the empty set, that sort of zero with a slash through it that you might remember from school. We use the empty set to indicate the null event, the impossible event. Remember? Now the elements on the list are 8. In mathematics, if we take a set, consider all its subsets, and include the empty set, we get what is called the power set. Our event space is nothing more than the power set of the sample space. If the sample space has a finite number of elements, say n, then its power set, that is, the event space, contains 2 raised to the power of n elements. More precisely, we can say that if the sample space has cardinality n, that is, it contains n elements, the event space has cardinality 2 raised to the power of n. The proof of this result isn't particularly complicated, but I will leave it to you if you are interested. In our example with ABC, the sample space has 3 elements, and its power set, the event space, contains 8 elements, which is exactly 2 raised to the power of 3. If the sample space is infinite, things get more complicated for the event space, whose number of elements is no longer simply 2 raised to the power of n, but let's not get into those details. Let's just say it is a somehow manageable issue. One small clarification. When we say the event space is nothing more than the power set of the sample space, we are simplifying a bit. More precisely, we should say that the event space is a subset of the power set of the sample space. In fact, we may want to refer only to certain subsets of omega, not necessarily all of them. Remember that for us, a subset of omega is an event of interest. For example, when we roll our die, we might be only interested in some events and not necessarily in all possible combinations of the single outcomes. In general terms, the event space brings together omega, the empty set, and all the simple and compound events we want to consider. But ultimately, it doesn't make sense to bore you with extensions, karatheodories, contributions, and so on. So, at least for now, while aware that it's a simplification, for us the event space is the power set of the sample space. That is, we consider all subsets of omega plus the empty set. And don't roll your eyes at me, I can see you. From a mathematical point of view, the event space we have defined as the power set of the sample space directly forms what is called a sigma algebra. If, on the other hand, we were to limit ourselves to a subset of the power set, we would have to verify this very important property. And what is a sigma algebra? Well, we will answer that in the next episode. For now, I will say goodbye. See you next time. Ciao ciao!